Lucene indexer in Lucene. Now we are focusing on Lucene index. Indexer. org.apache.lucene.index provides two primary classes: index writer, which creates and adds documents to indices, and index reader, which accesses the data in the index. Here you can see two main processing flow: index update and index search. Document indexing, here the given a document, add it into the index, and document retrieval for a given query, retrieve the most relevant document from the index. Here you can see raw data and parser in index update. Doc is connected to fields, and fields are connected to terms, and you can see the analyzer here. Lowercase removes stop words stemming, and index writer is connected to inverted index, and you can see the directory here, and index reader is connected to the inverted index. Here you can see statistics, delete, undelete docs, and inverted index is connected to the index searcher. Here you can see, and you can see the hits also, and filtered by Boolean model, is scored by a vector space model cosine. It says model cosine distance of query and doc, and controlled by boosting. Here query language, and here you can see the query parser. You can see the term query. You can see the query here: term query, trace query, Boolean query, range query. Query is connected to the fields, and fields are connected to the term. You can see analyzer here, and you can see the index searcher here. Here you can see Lucene indexing mechanism. Here to index data with Lucene, first of all we must convert it to a stream of plain text tokens. Therefore, other patterns of files must be converted into text before being indexed. Secondly, create a document object with its relevant field object, then call the method addDocument. To store the data for indexing. Next, use the specified analyzer to tokenize every word of indexes so that the data stream can be more suitable to be indexed. Last but not least, write the result back to the index files. The process of building full text indices is presented in this figure. Here you can see files to be indexed. Here .html, .text, .doc, .pdf. These are connected to document processing. Here you can see file patterns to be converted and addDocument. Document processing is connected to language analyzer. Language analyzer is connected to index files. Here you can see Lucene based full text search contains index management and search index. Its data handling process is like this figure. Here being indexed document is connected to exceedance analyzing logic. Text stream is passed from being indexed document to exceedance analyzing logic. Query sentences are connected to accidents analyzing logic. Text stream is passed from query sentences to accident analyzing logic. Accidents analyzing logic is connected to construct index logic. Meta word stream is passed from accidents analyzing logic to construct index logic. Accident analysis logic is connected to query sentences accidents analysis logic. Meta word stem is passed from accidents analyzing logic to query sentences accidents analyzing logic. And query sentences accidents analyzing logic is connected to index query logic. Query sentences object stream is passed from query sentences accidents analysis logic to index document query logic. Construct index logic is connected to storage abstract. Byte stream is passed from construct index logic to storage abstract. Index document is connected to storage abstract. Byte stream is passed from index document to storage abstract. Storage abstract is connected to index query index document query logic. Storage byte stream is passed from index storage abstracts to index document query logic. Index document query logic is connected to estimate and composer. Meta word stem is passed from index document query logic to estimate and composer logic. Estimate and composer logic is connected to query result. Text stream is passed from estimate and composer logic to query results. Here you can see inverted index implementation. First we can discuss about index structure. Both document and query is represented as a bag of words. In Apache Lucene, document is the basic unit for storage and retrieval. A document contains multiple fields, also called zones. Each field contains multiple terms equivalent to words. To control how the document will be indexed across its containing fields, a field can be declared in multiple ways to specify whether it should be analyzed, pre-processing step during index participate in the index, or stored in the case it need to be returned in the query result. Keyword not analyzed, indexed, stored. Unindexed, not analyzed, not indexed, stored. Unsorted, analyzed, indexed, not sorted. Text analyzed, indexed, sorted. Stored. In unstored, analyzed, indexed, and not stored. Inverted index is a core structure of the storage. It is organized as an inverted manner from terms to the list of documents which contains the terms. The list known as posting list is ordered by the global ordering, typically by document ID. To enable faster retrieval, the list is not just a single list but a hierarchy of skip list. This data structure is illustration here based on Lucene's implementation. It is stored on disk as segmented files, which will be both to memory during processing. Here the fields are connected to terms. Terms are connected to document frequencies, and terms are connected to documents. A term is connected to document, and document is connected to positions here list, and it has a term frequency, and document is connected to another document like that. Likewise here, and in index segment Lucene implementation, field definitions are here. field whether index and stored and offset, and this record is connected to this line is connected to field here, posting list, field term doc frequency, offset here 2, and it's connected to frequency here as a doc frequency, and offset here here it is 3, and this is connected to position here 1920 here. Here you can see the additional forward index. The whole index contain an additional forward index as here. Here the document is connected to fields, and fields connected to terms, and term you can see the term frequency here, and terms is connected to positions, and here you can see other documents. Here you can see indexing diagram. In Lucene index algorithm, two basic algorithms. One make an index for a single document, and two match a set of indices. Incremental algorithm maintain stack of segmented indices, create index for each incoming document, push new indices into the stack, and then merge. Optimization single doc indices kept in RAM saves system calls. Here b equal 3 and 11 documents indexed. Stack has 4 indices. Gray indices have been deleted. Five mergers have occurred here. You can see the document indexing here. In document indexing, the document in its raw form is extracted from a data adapter. This can be making an web API to retrieve some text output, or crawl a web page, or receiving an HTTP document upload. This can be done in a batch or online manner. When the index processing is start, it presses each raw document and analyze its content. A typical steps include tokenize the document, break down into words, lowercase each word to make it non-case sensitive, but need to be careful with names and abbreviations. Remove stop words, take out high frequency words like the, but need the careful with phrases. Stemming, normalize different form of same word. For example, reduce run, running, ran into run. Synonym handling, this can be done in two ways. Either expand the term to include synonyms. Its synonyms, that is, if the term is huge, add gigantic and big, or reduce the term to a normalized synonym, that is, if the term is gigantic or huge, changing it to big. At this point, the document is composed with multiple terms. Document equals term 1, term 2, etc. Optionally, the terms can be further combined into n-grams. After that, we count the term frequency with this document. For example, in a bigram expansion, the document will become document 1, doc 1 implies term 1 colon 5, term 2 colon 8, term 3 colon 4, term 1 underscore 2 colon 3, term 2 underscore 3 colon 1. we may compute a static score based on some measure of the quality of the document. After that, we insert the document into posting list. If it exists, otherwise create a new posting list for each terms of n-grams. This will create an inverted list structure. There is a boost factor that can be set to the document or field. The boosting factor effectively multiply the term frequency, which effectively affecting the importance of the document or field. Document can be added to the index in one of the following ways: inserted, modified, and deleted. Typically, the document will first added to the memory buffer, which is organized as an inverted index in RAM. When this is a document insertion, it goes through the normal indexing process to analyze the document and build an inverted index list in RAM. When this is a document deletion, the client request only contains the doc ID. It reflects the forward index to extract the document content, then goes through the normal indexing process to analyze the document, build the inverted list. But in this case, the doc object in the inverted list labeled as deleted. When this is a document update, the client request contain the modified document. It is handled as a deletion followed by an insertion, which means the system first fetch the old document from the forward index to build an inverted list with nodes marked deleted, and then build the new inverted list from the modified document. For example, if doc1 equal AB is update to AC, then the posting list will be A colon doc1 deleted implies doc1, B colon doc1 deleted, C colon doc1. After collapsing A, the posting list will be A colon doc1, B colon doc1 deleted, C colon doc1. As more and more documents are inserted into the memory buffer, it will become full and will be flushed to a segment file on the disk. In the background, when M segments have been accumulated, Lucene merges them into bigger segment files. Notice that the size of the segment files at each level is exponentially increased. M to the power 2, M to the power 3. This maintains the number of segment files that need to be searched per query to be at the big O log n complexity, where n is the number of documents in the index. Lucene also provides explicit optimize call that merges all segment files into one. Here let's details a bit on the merging process. Since the posting list is already vertically ordered by terms, and horizontally ordered by doc ID, merging two segment files S1 and S2 is basically as follows. Walk through the list of both S1 and S2 together in the walk the posting list from both S1 and S2 together in shorter term order. For those non-common terms that appeared in one of S1 or S2 but not both, write out the posting list to a new segment S3. Until we find a common term T, we merge the corresponding posting list from these two segments. since both lists are sorted by doc ID, we just walk through both posting lists to write out the doc object to a new posting list. When both posting lists have same doc, which is the case when the document is updated or deleted, we pick the latest doc based on the time order. Finally, doc frequency of each posting list of the corresponding term will be computed. Here you can see merge factor equal m and can explicitly call index writer dot optimize to merge all segment into one single document. Here you can see doc1, doc2, doc3 is connected to memory buffer posting list. After m documents are added, write out the posting list to the index segment here, level 1, and clear the memory buffer. Here the memory buffer is connected to index segment, here level 1, and index segments of level 1 are connected to index segments of level 2. If there is already m segments at level 1, step 1, merge m segments level 1 to a new segment of level 2 and clear the m segments of level 1. And here you can see hold the index of m documents here and hold the index of m to the power 2 documents here, and index segments of level 2 are connected to index segments of level 3 here, and here holds the index of m to the power 3 documents here. Here in for large, here you can see document partitioning. For large corpus like web documents, the index is typically distributed across multiple machines. There are two models of distribution: term partitioning and document partitioning. In document partitioning, documents are randomly spread across different partitions where the index is built. In term partitioning, the terms are spread across different partitions. We will discuss the document partitioning as it's the most commonly used. Distributed index provided by other technologies that is built on Lucene, such as Elasticsearch. A typical setting is as follows. In this setting, machines are organized as columns and rows. Each column represents a partition of documents, while each row represents a replica of whole corpus. During document indexing, first row of the machine is randomly selected and will be allocated for building the index. When the new document is crawled, a column machine from the selected row is randomly picked to host the document. The document will be sent to this machine where the index is being built. Updated index will be later propagated to other rows of replicas. During document retrieval, the first row of the replica machine is selected. The client query will then broadcast to the every column machine of the selected row. Each machine will perform the search on its local index and return the top M elements to the query processor, which will consolidate the result before sending back to the client. Notice that k divided p less than m less than k, where k is the top k documents the client expects and p is the number of columns of the machine. Notice that m is the parameter that needed to be turned. One caveat of this distributed index is that as the posting list is split horizontally across partitions, we lost the global view of IDF value, without which the machine is unable to calculate TF-IDF score. There are two ways to mitigate that. Do nothing. Here we assume the document is evenly spread across different partitions to the local IDF represent a good ratio of the actual IDF. 2 extra round trip. In the first round, query is broadcast to every column of the return to its local IDF. The query processor will collected the IDF response and compute the sum of the IDF. In the second round, it's broadcast the query along with the IDF sum to each column of the machine, which will compute the local score based on the sum. Here you can see term partitioning, machine T1, term 1, term 2, machine T2, term 3, term 4, term 5. And here you can see machine D1, doc 1, doc 2. Here machine D2, this is document partitioning. Machine D2, doc 3, doc 4, doc 5. Here machine D3, doc 6, doc 7. This is about distributed index here. And here you can see a client query and pick a random row and scatter together, and this is connected to partition 1 replica, partition 2 replica, partition 3 replica. Here you can see the row 1 and row 2. Here you can see the crawler randomly pick one, and here you can see the indices, and here you can see the inverted index. Here this inverted index connected to this one, and here this inverted index is connected to this one of the row 1, and this here the partition 3, the inverted index is connected to this one. Here you can see the structure of Lucene index. The Lucene index is stored in a single directory in the file system on a hard disk. The core element of the Lucene index are segments, documents, fields, and terms. In Lucene index, every index consists of one or more segments. Each segment contains one or more documents. Each document has one or more fields, and each field contains one or more terms. Each term is a pair of string representing a field name and a value. So a segment consists of series of files. Pictorially, the entire structure of a Lucene index can be represented as shown in this figure here. Exact number of files that constitute each segment varies from index to index and depends on the number of fields that the index contains. All files belonging to the same segment share a common prefix and differ in the suffix. One can think of segment as a subindex, although each segment is not fully independent index. Here you can see the index here. Segments is inside index, and document or documents are inside segments, and here the in segment, and fields. So fields are in documents, and terms are in fields, and pair of strings are in term. Field name and field value are in pair of strings. Now we are considering Lucene index. A Lucene index is an inverted index. An inverted index means that the content of the documents that are analyzed has their important terms indexed as a pair consisting of a field name and a field value. A field contains many terms that point to the corresponding document. To summarize, an inverted index makes the process of retrieving documents from a system breeze. Finally, the documents are searched in the fields and their values. A Lucene index consists of many segments. A segment is created every time when new document is created and indexed. Hence, each segment has many documents stored in it. The document consists of index fields. An index field is a pair consisting of a field name and field value pairs. Fields are used for calculating weights and ranking each search result. Here you can see the index is connected to segments. Segments is connected to documents, and document is connected to here fields. Here you can see the Lucene indexing architecture. The entire indexing procedure can be summarized as shown in this figure. Here the source data is connected to source specific parser, and it is connected to PDF parser, HTML parser, XML parser, user defined parser. Source specific parser is connected to analyzer, and it is connected to white space, simple, standard, etc. And analyzer is connected to index. Here you can see the basic internal structure of an index. This figure shows the basic internal structure of an index. The data in a segment is represented abstractly rather than as a realistic representation of actual data structure. Index. This is similar conceptually to database table, but differ in some important ways. The table in traditional relational database or NoSQL database needs to at least have its scheme defined when it is created. There are some clear constraints on the definition of the primary key, columns, and the like. However, there are no such constraint in Lucene index. Lucene index can be understood as a document folder. You can put a new document into the folder, or you can take one out. But if you want to modify one of the document, you must first take it out, modify it, and then put it back in the folder. You can put all sort of document in the folder, and Lucene can index the document whatever the content. Document similar to a row in a relational database. So a document in a document database, an index can contain multiple documents. A document written into an index is assigned a unique ID. That is the sequence number, more usually called doc ID. Sequence numbers are doc ID field. One document is made up of one or more fields. A field is the smallest definable unit in data index in Lucene. Lucene provides many different types of field, including string field, text field, and numeric data values field. Lucene determines the type of indexing, such as inverted index, stored field, docked values, or n-dimensional, to use for the data depending on the field type, the type of the field type. Field and field type field type. The term and term dictionary, smallest unit of index and the search in Lucene. Field consists of one or more terms. The term is produced when a field is put through an analyzer, tokenizer. The term dictionary is the basic index used to perform conditional searches on terms. Segment. An index is composed of one or more sub-indexes. A sub-index is called segment. The conceptual design of segment in Lucene is similar to LSM, but there are some differences. They inherit the data writing advantage of LSM, but only provide near real-time but not real-time queries. When Lucene writes the data in first write to a in-memory buffer similar to memtable in LSM but not readable. When the data in the buffer reaches a certain amount, it will be flushed to become a segment. Every segment has its own independent index and are independently searchable, but the data can never be changed. This scheme prevents from random writes. Data is written as batch or as an append or achieves a high throughput. The documents written in segment cannot be modified, but they can be deleted. The deletion method does not change the file in its original internal location, but the doc ID of the document to be deleted is saved by the another file to ensure that the data file cannot be modified. Index queries need to query multiple segments and merge the result, as well as handling deleted document. In order to optimize queries, Lucene has a policy to merge multiple segments, and in this regard is similar to LSM's merge of SS table. Before segments are flushed or committed, data is stored in a memory and is unsearchable. There is another reason why Lucene is said to provide near real-time and not real-time queries. After reading the code, the reason for this is the searching of data in Lucene relies on the index setup. For example, the inverted index relies on term dictionary, and the data index in Lucene is set up during segment flush and not in the real time. The purpose of this is to set up the most efficient index. Naturally, it can introduce another index mechanism that set up the index in real time as it is written, but implementation of such mechanism would differ from the current index in the segment, needing the introduction of extra index at the right time, and an extra query mechanism involving some degree of complexity. Sequence number is called doc ID. Is an important concept of Lucene. The database uniquely identifies a row using primary key, while Lucene index uniquely identifies the doc by its doc ID. However, the following points should be kept in mind. One, the doc ID is not actually unique to index, but is unique to a segment. Lucene does this mainly to optimize the writing and compression. Since it is only unique to a segment, how can a doc be uniquely identified at the index level? The solution is simple. The segments are ordered. To take simple example, an index has two segments, and each segment has 100 docs. Respectively, the doc IDs in segment are 0 to 100, but when they are converted to the index level, the range of doc IDs in the second segment is converted to 100 to 200. Doc ID is unique within a segment, numbered progressively from 0, but this does not mean the doc IDs are continuous. When a doc is deleted, there is a gap. 3. The doc ID corresponding to a document can change, usually when segments are merged. The inverted index, a very core of Lucene, is essentially list mapping each term to the doc IDs of the document containing the term. So when Lucene is searching internally, it makes a two-phase query. First phase is to list the doc IDs found to contain the given term. So when the Lucene is searched, and the second phase is to find the doc based on the doc ID. Lucene provides functionality to search by term as well as to query on the basis of doc ID. Doc ID is basically an int32 value starting from 0, which is an important optimization. Also reflected in the compression and query efficiently. This includes such optimization as a delta policy for data compression, zigzag code, skip list used in inverted index list. These are here you can see doc in-memory buffer segments, and segments are in index. Doc is connected to in-memory buffer via add document, and in-memory buffer is connected to segments via flush. Here the as an example, here segment 0, 1 and 2 is connected to segment 4 via merge. Here the in a segment you can see doc IDs and doc, and here the as an example here the doc ID 4, the doc 4 is connected to here doc 4 here. It has fields and values. Here you can see the basic relationships between different types of fields and fields in Lucene. Index supports Lucene supports many types of field, and each type of field determines the supported data type and index modes. Currently, the supported field types include long point, text field, string field, and numeric doc values field. This figure shows the basic relationship between different types of field in Lucene. All field types inherited from the class field. The field has three main attributes: name, string, and field data, bytes ref, and type, field type. Attribute name is the name of the field. Field's data is the name of the value. The value of all types fields are ultimately represented as binary byte streams. The attribute type is the type of field which determines how field is indexed. Field type is an important class containing many important attributes. The value of these attributes decide how the field is indexed. Lucene provides many many types of fields. There are two essential differences. First difference is the different types of values in the field define different conversion methods, and the second is the defining combination of different values in different attributes of field types. In this mode, you can customize types using custom data and combining the index parameters in the field type. You only have to understand specific meaning of each attributes in the field type to know what index mods Lucene can provide. Let's look at them one by one. Stored indicates whether to save the field. If false, Lucene does not store the value of the field, and document returned in the query result will only contain saved field. Tokenized represent whether or not to tokenize. In Lucene, only a text field needs to be tokenized. Term vector. Here we explain the concept of term vector, that simply put, the term vector saves all information related to term, include term value, frequencies, positions. It is per document inverted index and provide functionality to find all term information in the document according to doc ID. It is not recommended to enable term vector for short fields because all the term information can be obtained by tokenizing once again. However, it is recommended to enable term vector for longer fields, so fields with the high cost tokenization. There are two main uses of term vector. First is keyword highlighting, and the other one is similarity matching between documents, more like this. Omit norms. Norm stands for normalization. Lucene enables every field in every document to have normalization factor saved. This is a coefficient related to scoring during searches. It only takes 1 byte to save the norms, but separate norm is saved in every field of every document, and every piece of norms data is loading into memory. So enabling norms consumes additional storage space and memory, but if you disable norms, you cannot use index time boosting. Elasticsearch officially recommends using query time boosting instead than length normalization. Index options. Lucene provides 5 optional parameters for inverted index: none, docs, doc and fix, docs and freaks and positions, and doc and freaks and positions and offsets, which are used to select whether the field needs to be indexed and what content to index. Doc values type. Doc value is an forwarded index introduced in Lucene 4.0 doc ID to field column store, greatly enhancing the efficiency of sorting, faceting, and aggregation. Doc values is a storage structure with a strong schema, so all fields with doc values enabled must have exactly the same type. Currently, Lucene only provides 5 types of numeric binary: sorted numeric, and sorted set. Dimension. Lucene supports indexing of multidimensional data, employing special indexing to optimize querying of multidimensional data. Most typical usage scenario of this type of data is the index geographical location. This is an indexing method generally used for latitude, longitude data. Here you can see the subtypes, fields, long point, subtype field, long point, string field, text field, numeric, doc, value field, and here you can see the string name, byte ref, field data, field type. See the field types: stored, tokenized, term vector. Here with under term, store term vector, store term vector, offset, store term vector, position, store term vector, payload. And omit norms, index options, doc value types, and dimensions. Dimension count, dimension num bytes. Here you can see the structure of Lucene segment. Here the Lucene 4.0 we are considering. Lucene uses a well-known inverted index representation with additional functionality of keeping adjacent non-inverted data on per document basis. Both in-flight and persistent data uses variety of encoding schema that affect the size of the index's data and the cost of data compression. Lucene uses pluggable mechanism for data coding and for actual storage of index data. Directory API. incremental updates are supported and stored in indexed extent, refers to as segments that periodically merge into larger segment to minimize the total number of index parts. The document model document model, the documents are modeled in Lucene as a flat ordered list of fields with the content. Fields have name and content data, float weight used for scoring, and loose letter for scoring, and the other attributes depending on the type, which together determine how the content is processed and represented in the index. There can be multiple fields in the same name in the documents. In which they can or will be processed sequentially. Documents are not required to have a unique identifier, though they often carry a field with this role for application level unique key lookup. In the process of indexing, document are assigned internal integer identifiers. Field types, there are two broad categories of fields in Lucene document. Those carry content to be inverted, indexed field, and those which content of the to be stored as is the stored field. Fields may belong to either or both categories, for example with content both to be stored and inverted. Both index and stored fields can be submitted for storing and or indexing, but only stored fields can be retrieved. The inverted index can be accessed as and traversed being using a specialized API. Index fields can be provided in plain text, in which the case it will first pass through a text analysis pipeline, and it is or in its final form of a sequence for tokens of tokens with attributes, so-called token stream. Token streams are then inverted and added to the in-memory segments, which are periodically flushed and merged depending on the field options. Various token attributes such as positions, starting or coding offset or per position payloads are also stored in the inverted data. It is possible, for example, to omit positional information while still storing the in-document terms frequencies. On per field basis, a variant of an index field is a field where the creation and storage of term frequency vectors are requested. In this case, the token stream is used also for building a small inverted index consisting of data from current field only, and this inverted data is then stored on the per document or per field basis. Term frequency vectors are particularly useful when they perform in document highlighting or relevance feedback, or when generating search result snippet region of the text that best matches the query terms. Stored fields are typically used for storing auxiliary per document data that is not searchable but would be cumbersome to obtain otherwise. For example, it would require retrieval from a separate system. This data is stored as byte arrays but can be manipulated through a more convenient API that present it as a UTF-8 strings, numbers, arrays, etc. Or optionally it can be stored using strongly typed API, so-called doc values, that can use more optimized storage format. This kind of strongly typed storage is used for example to store per document per field weight, so-called norms, and they typically are responded to corresponded to field length normalization factor that affects scoring. Here you can see segment info, field info, live docs bit set, per document field data, per document inverted data in segment. Here the segment info, commit metadata, segment stats, and here then you can see field info, field metadata. Field info interacts with per document field data and per term inverted data. Stored values, term vectors in document frequencies plus positions. Scoring and scoring values norms are in per document field data. Term dictionary plus doc frequencies, and per document term frequencies and per position attributes are in per term inverted data. Here you can see a term dictionary plus doc and frequencies. Here more descriptive, and inside it there's a per document term frequencies, and inside it per position attributes. Here you can see live docs or bit set deletions. Here you can see indexing process in here we are considering Lucene 4.0. The resulting token stream is finally processed by indexing chain. And the supported attributes, term value, position, offset, and payload data are added to the respective posting list for each term. Term values don't have to be UTF-8 strings as in previous versions of Lucene. The version 4.0 fully supports arbitrarily byte array values as terms and can use custom comparators to define the sorting order of such terms. Also at this stage, documents are assigned to their internal document. Document identifiers, which are small sequential integers for efficient delta compression. These identifiers are ephemeral. They are used for identifying document data within a particular segment, so they naturally change after two or more segments are merged during index compaction. Here you can see the tokenizer. It's connected to field value, field 1, doc1 are connected to here to the tokenizer. You can see term, position, offset, payload, and custom in tokenizer, and it is connected to token filters via token stream with modifiable attributes. Token filters are connected to document inverter. Here you can see the indexing chain and in-memory segment here. And a document inverter is connected to term vectors and posting list. Here you can see the term vectors, and here you can see the posting lists. Here the token filter is connected to document content via field 1 and field doc in this example. Via field 1 and doc 1. Now we are considering a prefix tree in spatial indexing. The spatial module is based on spatial 4.4j and Apache license library that provides implementation of various shapes such as points, rectangles, and circles, and additionally support polygons with an extra dependency. Spatial strategy is the core interface used to interact with spatial module index spatial data and perform spatial queries. Spatial strategy define the way to index and query based on shapes. From Lucene Java docs, the points defined by spatial strategy as follows. Can it fix more than one shape or field? What type of shapes to be indexed? What type of query shapes can be used, and what types of query operations are supported. This might vary per shape. Remember that the different shape is attempted to be indexed than what is defined by corresponding spatial strategy, and exception will be thrown. Prefix trees from the foundation of spatial index data structures in Lucene. Prefix trees act as a tree data structure where shapes are decomposed into strings. Each string representing a rectangular spatial region. This figure shows a prefix tree of words car, cat, do, and don. Car, cat, do, and don. Lucene defines an abstract class, a spatial prefix tree, which represent abstract representation of the prefix tree. This class defined all necessary methods such as getting the number of levels, getting a cell at level, and so on. There are that are required for working with prefix trees during searches. As the Lucene consists of two concrete implementation: spatial prefix tree, quad prefix tree, and geohash prefix tree. Here you can see root is connected to C, and C is connected to A, and A is connected to R, and then I is connected to end car. Here C is connected to A, and A is connected to T, and T is connected to N, is cat. And here the root is connected to D, and do is connected to D is connected to O, and O is connected to N, and it's do. And here do is connected, D is connected to O, and O is connected to N, and N is connected to N, is done here. Here you can see a quad tree. A quad tree is a spatial data structure where each node has exactly 4 children. Quad tree splits a spatial dimension into 4 each time a new level is added to the tree. Quad trees are notable for 2 use properties. Higher level nodes of quad tree help representation of oral data in a less granular level. That is, a depth of detail stored in the top level is less than that stored in the leaf level nodes. Quad trees are great for searching 2-dimensional spaces. For example, given a 2-dimensional space, to find the point closest to the given coordinates, a simple traversal of quad tree will lead to the result. Here you can see a quad tree. Here root is connected to A here, and here is connected to a node, and it's another connected to node, and this one is connected to B, C, D, and E. Here this one is connected to another node, then S, K, and L. Here this node is connected to G, H, I, and L. Oh, this one here. Here you can see a KD tree in spatial indexing. A KD tree is a space partitioning tree that's allow splitting a plane of space into k-dimensional space. A KD tree is a binary tree which with each node representing a k-dimensional point. But put simply, given a collection of points, a range is split using an axis value. For example, if a node represents x-axis and split using x-axis is done, the left behind all the points that have an x-axis value less than the split value, the right tree having all values greater than the same one. The KD trees prove useful for variety of query types such as point and range queries. For this reason, they are important member of Lucene's indexing capabilities. This figure shows an example of a KD tree. Lucene implementation uses block KD, BKD tree, which is an efficient version that is IO friendly and restricts IO usage. Here you can see A is connected to B and C is connected to D and D is connected to E and F. Here you can see a BKD tree in spatial indexing. BKD trees are built in the same manner as KD trees, recursing and partitioning the n-dimensional space and performing an equal split at each recursion. However, BKD trees stop recursing once there are fewer than 1024 points. At that point, all points are written to one block on the disk. When a point is indexed in the BKD tree, it is converted into an equivalent byte array representation. Lucene then buffers the points being indexed and then writes them to using a points format. All default Lucene codecs now support the points being indexed. As evident in this figure, a BKD tree is a KD tree with B tree incorporated into it. Nodes have compressed keys and their children define key ranges with equivalent pointers to their children. You can see here the BKD tree. Here you can see a Lucene 9.5 file format. Here the index structure overview. Here you can see the index structure overview in Lucene 9.5 file format. Each segment index maintains the following. Segment info. This contains metadata about a segment which has the same number of documents, what files it uses, and information about how segments is stored. Field names. This contains metadata about the set of named field used in the index. Stored field values. This contains each document a list of attributes value pairs where the attributes are field names. These are used to store auxiliary information about the document such as title, URL, or an identifier to access databases. The set of stored fields are what is returned for each hit when searching. This is keyed by document number. The term dictionary, a dictionary containing all of the returns, all of the terms used in all index field of all the documents. The dictionary also contains a number of documents which contain the term. The pointers to the term frequently are proximity data. Term frequency data for each term in the dictionary, numbers of all documents that contain that term, the frequency of the term in the document unless frequencies are omitted, index_docs. Term proximity data for each term in the dictionary, the position of the term occurs in each document. Note that this will not exist all fields in the all document omit position data. Normalization factors, for each field in each document the value is stored that is in multiplied into score it for hits on that field. Term vectors, each field in each document, the term vector, sometimes called document vector, may be stored. The term vector consists of terms text and term frequency. To add the term vectors to your index, see the field constructors. Per document values, like stored values, these are also keyed by document number but are generally intended to be loaded into the main memory for fast access, whereas the stores values are generally intended for summary result for searches. Per document values are useful for things like scoring factors. Live documents, an optional file indicating the document, which document is live. Point values, the optional pair of fields recording dimensionally index field to enable fast numeric range filtering and large numeric values like big integer and big decimal, 1D and geographic shape intersection, 2D and 3D. Vector values, the vector normal format stored numeric vectors in a format optimized for random access and of computation, supporting high dimensional nearest neighbor search. Here the class Lucene 90 segment info format in package of.apache lucene.codex. Lucene 90, the Lucene 9.0 segment info format. Here the class Lucene 9.94 field info format in package of lucene.codec.lucene 9.0 field info format. Class Lucene 90 stored field format in package of lucene.codec.lucene 9.0 stored field format. Class Lucene 90 posting format in package of lucene.codex.lucene 5.0 posting format, which encodes posting in fact integer blocks for fast decode. Class Lucene 90 posting format in org.apache.lucene.codex.lucene the Lucene 5.0 posting format, which encodes posting in fact integer block for fast decode. Class Lucene 90 posting format in package of lucene.codex.lucene 5.0 posting format, which encodes posting in a fact integer block fast decode. Class Lucene 90 forms norms format package in package of lucene.codex.lucene 9.0 is core normalization format. Lucene 9.0 term vector format in package of lucene.codex.lucene the Lucene 9.0 term vector format. Class Lucene 90 doc values format in package of lucene.codex.lucene 9.0 doc values format. Class Lucene 90 live docs format in package of lucene.codex.lucene 9.0 live doc format. Class Lucene 90 points format in package of lucene.codex.lucene 9.0 point format, which encodes dimensional values in a block KD tree structure for fast 1D range and in dimensional shape intersection filtering. Lucene 95 HNSW vectors format in package of lucene.codec.lucene 95 vector format, which encodes numeric vector values and optional associated graph connecting the document having values. The graph is used to power HNSW search. The format consists of three values: .vect file, .vex file, and .vem file. Here you can see the structure segment info field value stored field value, term dictionary, term frequency data, term proximity data, normalization factors, term vectors, per document values, live documents, point values, and vector values. Here you can see the summary of file extension in Lucene 9.55 format. Following table, this table summarizes the name and extension of the files in Lucene. Lucene file names by extension. Here the name segment files, extension segment underscore n. It stores information about commit point. Log file, write.log here. Write log prevents multiple index writers from writing the same file. Segment info stores metadata about the segment. Compound file, an optional virtual file consisting of all the index files for systems that frequently run out of file handles. Fields stores information about the fields. Field index contains pointers to field data. Field data stored fields for documents. Term dictionary, the term dictionary stores term info. Term index, the index into the term dictionary. Frequencies contains a list of docs which contain each term along with frequency. Positions stores position information about where the term occurs in the index. Payload stores additional per position metadata information such as character offset and user payload. Norms encodes length and boost factors for docs and fields. Per document values encodes additional scoring factors or other per document information. Term vector index stores offset to the document data file. Term vector data contains term vector data. Live documents info about what documents are live. Point values hold index point. Vector values hold index vectors. .vect files contain the raw vector data and .vem the vector metadata. Example, we can consider package org.apache.lucene.index. This is a code to maintain and access indices. As an example 2, we can consider this code segment here, index writer, class index writer, and index writer create and maintains an index. Here the index writer config holds all the configuration that is used to create index and index writer. Once index writer has been created with this object, changes to this object will not affect the index writer instance. For that, use live index writer config that is returned from the index writer get config index writer get config. And here you can see add document method. This adds a document to index, and index close all open resources and releases the write lock. And this index writer class is in the package org.apache.lucene.index. Here you can see the class fields provides the terms index for fields that have it and list which fields do. This is primarily an internal experimental API, C fields producer, although it is also used to expose the set of term vectors per document. This is in package org.apache.lucene.index. In index reader is an abstract class providing an interface for accessing a point in time view of an index. Any changes made to index via index writer will not be visible until new index reader is opened. It is best to use directory reader.open index writer to obtain an index reader if your index writer is in process. When you need to reopen to see any changes in the index, it's best to use directory reader.open if change directory reader, since a new reader will share resources with previous one when possible. Search of an index is done entirely through its abstract interface, so that any class which implement is searchable. Here you can see the method of index reader get term vectors. This retrieves term vectors for this document, or null if term vectors were not indexed. Here access index field for an index segment, and here access term vector fields for a specified document. Here this code segment is related to terms. Terms, the class term access to terms in a specified field. Here has positions, returns the true if the documents in this field store position. Here has offsets, returns true if the document in this field store offsets. Has payloads, returns true if the document in this field store payloads. Here the terms enum iterated to seek or step through terms to obtain frequency information for the current term. Here the iterator returns an iterator that will step through all terms here. Here in the next here in the byte ref represent byte array that as a slice offset plus length into an existing byte array. The bytes member should never be null. Use empty underscore bytes if necessary. Here in next increment the iteration to the next bytes ref in the iterator, returns the resulting byte ref or null if the end of the iterator is reached. Returns the resulting byte ref and or null if the end of the iterator is reached. The return byte ref may be reused across all next across call to next. After this method returns null, do not call again. The results are undefined. Here in the term returns the current term. So here we are getting metadata about the field here, position, offset, payload, and iterate through the terms here. And the class term is in the package org.apache.lucene.index. Here a term represent the collection of terms within a field, exposes some metadata and statistics, and the API for enumeration. Here with the documents, here you can see the post class posting enum is a variable, iterates through the postings not you must first call the doc id set iterator dot next doc before using any of the per doc methods. This is in the package org.apache.lucene.index. The posting enum is an extension of doc id select set iterator that iterates over a list of documents for a term along with the term frequency within that document. With regarding positions, here you can see a class posting enums iterate through the postings. Not you must first call doc id set iterator dot next doc before using any of the pre-doc methods. Posting enum also allows iteration of positions. A term occurred within the document. Any additional per position information, offsets, and payloads. The information available is controlled by flags passed to term enum postings. This postum enum is in package org.apache.lucene.index. As an example 7, we can consider this one. This is from RabbitTalk. This following index definition would allow using Lucene index for this query. Org supports Lucene based indices to support both property constraint and full text constraint. Depending on the configuration of a Lucene index, can be used to evaluate property constraint, full text constraints, or path restrictions and shorting. You can see the query here. This index definition would allow using Lucene index for this query. The index definition node for Lucene based index must be of type query index definition, must have a type property set to Lucene, must contain the async property set to value async. This is what sent the index update process to background thread. Note that compared to property index, Lucene property index is always configured in async mode, hence it might lag behind the reflecting the current repository state while performing the query. Here as an example 8, you can see the index reader here, the class index reader. Index reader is an abstract class providing an interface for accessing a point in time view of an index. Any changes made to the index via index writer will not be visible until new index read is opened. It is best to use in directory read dot open index writer to obtain an index reader. If your index writer is in progress, when you need to reopen to see changes in the index, it's best to use directory reader dot open if change directory reader, since the new reader will share resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that any subclass which implement is searchable. This is in package og.apache.lucene.index. This is open existing index here. As an example, now we are considering index writer in index APIs in package og.apache.lucene.index. Index writer is used to create an index and to add, update and delete documents. The class index writer in package og.apache.lucene.index, and index writer creates and maintains an index. Index writer is used to create an index and to add, update and delete documents. The index writer class is thread safe and enforces a single instance per index. Creating an index writer creates a new index or open an existing index for writing in a directory depending on the configuration of index writer config. A directory is an abstraction of typically represent a local file system directory. Various implementation of FS directory, but it may also stand for some other storage such as RAM. Now we are considering field types. Stored field values are retrieved by a searcher using implementation of stored field visitor. Class stored field visitor in package og.apache.lucene.index provides a low-level means of accessing the stored field values in an index. Lucene supports a variety of different documents field data structures. Lucene's core and inverted index is comprised of postings. The posting with their term dictionary can be thought of as a map that provides sufficient efficient lookup given a term, roughly a word or token, to ordered a list of documents containing that term codex. Additionally, record impacts alongside posting in order to be able to skip over low scoring documents at the search time. Posting do not provide any way of retrieving terms given a document short of scanning the entire index. Stored fields are essentially the opposite of postings, providing efficient retrieval of field values given a doc ID. All stored field values for a document are stored together in a block. Different types of shorted stored field provide high-level data types such as strings and numbers on top of underlined bytes. Stored field values are usually retrieved by searcher using implementation of stored field visitor. Doc values field are what are sometimes referred to as columnar or column stride fields by analogy to relational database terminology, in which documents are considered as rows and fields and columns. Doc values fields store values per field. The value for every document is held in a single data structure, providing for rapid sequential lookup of a field given a doc ID. These fields are used for efficient value-based sorting and for faceting, but they are not useful for filtering. Point values represent numeric values using a KDT data structure. Efficient one and higher dimensional implementation make these the choice for numeric range and interval queries and geospatial queries. Now we are considering fields in postings API. Field is the initial entry point into the posting API. This can be obtained in several ways. The class fields in package og.apache.lucene.index provide a terms index for fields that have it and list which fields do. This is primarily an internal or experimental API, although it is also used to expose the set of term vectors per document. Here the fields implement Java iterable interface. So it's easy to enumerate a list of fields here. Here the access index fields for index segment. The access term vector fields for specified document. So enumerate a list of fields. Access the terms for this field. Here you can see terms. The terms represents collection of terms within a field, exposes some metadata and statistics and API enumeration. The class terms in package org.apache.lucene.index access to the terms in a specific field. Here the term enum provides an iterator over the list of terms within a field. Some statistic about the term and methods to access terms, documents, and positions. Here the metadata about the field. Here the iterate through term. Seek the specific term. Get the document frequency and enumerate through the documents, and enumerate through the documents and position. The documents now, the posting enum is an extension of docid settled iterator over the list of documents for a term along with the term frequency that within that document. Here the class posting enum in package.apache.lucene.index iterates through the postings. Note that you must first call the docid iterator set iterator next doc before using any of the pre-doc methods. Posting enum is an extension of docid iterator that iterate over the list of document of for a term along with the term frequency within that document. Positions postings enum also allows iteration of postings a term occurred within a document or any additional per position information, offset, and payload. The information available is controlled by flags passed to the terms enum postings. Now we are considering term statistics in index statistics. Term enum.docfreq method returns the number of documents that contain at least one occurrence of the term. This statistics is always available for an index term. Note that it will also count deleted documents when segments are merged. The statistics is uploaded as this deleted document are merged away. Term enum.total term freq method returns the number of occurrences of this term across all documents. Like docfreq method, it will also count occurrences that appear in the deleted documents. Now we are considering introduction in Apache Lucene index file format in package.apache.lucene.codex.lucene95. This here we are define the index file format used in this version of Lucene. If you are using different version of Lucene, please consult the copy of the docs that was distributed with the version you are using. Now we are considering document numbers in definition. In particular, numbers may change in the following situations. Internally, Lucene refers to documents by an integer document number. At first, the document added to an index is numbered 0, and each subsequent document added gets a number 1 greater than the previous. Note that the document number may change, so caution should be taken when storing these numbers outside the Lucene. In particular, numbers may change in the following situations. A number is stored in each segment are unique when within the segment, and must be connoted before they can be used in a larger context. The standard technique is to allocate each segment of range values based on the range of numbers used in the segment. To convert a document number for a segment from segment to external value, the segment-based document number is added. To convert an external value back to the segment-specific value, segment is identified by the range that external value is in. The segment-based value is subtracted. For example, 5 document segment might be combined so that the first segment has the base value of 0 and the second of 5. Document 3 from the second segment would have been an external value of 8. When the documents are deleted, gaps are created in the numbering. These are eventually removed as the index evolves through merging. Deleted documents are dropped when segments are merged. A freshly merged segment has thus no gaps in the numbering in its numbering. Now we are considering file naming. All files belongs to a segment have the same name with the varying extensions. The extensions correspond to a different file formats. When using a compound file format, default for all small segment, these files except for the segment info file and log file and deleted document file are collapsed into a single .cfs file. Typically, all segments in an index are stored in a single directory, although it is not required. File names are never reused. That is, when any file is saved to the directory, it is given a never before used file name. This is achieved using simple generations approach. For example, the first segment file is segment _1, then segment _2, etc. Generation is a sequential long integer represented in alphanumeric base 36 form. Now we are considering log file. If the directory is different from the index directory, then the write log will be named xxx-write.log, where xxx is a unique prefix derived from full path to the index directory. The write log, which is stored in the index directory by default, is named write.log. If the log directory is different from the index directory, then the write log will be named xxx-write.log, where the xxx is a unique prefix derived from the full path to the index directory. When this file is present, a writer is currently modifying the index, adding or removing documents. This log file ensures that only one writer is modifying the index at a time. Now we are considering Lucene 9.7.0 Facet API. Lucene 9.7.0 Facet API provides facet indexing and search capabilities. Now we are considering index time joins in Lucene 9.7.0 join API. It's Lucene's join module. This query should be used after main query has been executed. For each hit, execute the parent children block join query. The class parent children block join query in package lucene.search.join. This query that returns all the matching child documents for a specific parent document index together in the same block. The provided child query determines the matching child docs is been returned. The index time joining supports joins while searching, where joins document are indexed in a single document block using indexWriter.add documents. This is useful for any normalized content, XML documents or database tables. In database terms, all rows for a join table matching a single row is the primary table must be indexed in as a single document block. With the parent document being last in the group. When you are indexing this way, document in your index are divided into parent document, last document for each block, the child document, all others. You provide a bits set provider that identify the parent document, as Lucene does not currently record any information about doc blocks. At search time, the two parent block join query to remap join matches from any child query, that is a query that matches only child document up to the parent document space. Resulting query can be then used as a clause in any query that matches parent. If you care about what child documents matched for each parent document, then the parent children block join query to matched parent document retrieve the child document that caused to match the parent document first place. This query should be used after main query has been executed. For each it executes the parent child children block query. So to map or join in the position direction, use two child block join query which wraps any query matching parent document, creating the joint query matching only child index. So this is basically with Lucene search module, but I included this here as an example due to the indexing. Do you see the importance of indexing here? Run the parent block join query to figure out top matching children nodes. Process top child hit. Now we are considering Lucene 9.7 memory API. Here the class memory index in package org.apache.lucene.index memory, high performance single document memory Apache Lucene full text search index in the package, and the memory API is for the memory. And the class memory index, that's high performance single document main memory Apache Lucene full text search index. Here you can see an example usage. This class is a replacement. Here the memory index is a replacement subject for RAM resident directory implementation. It is designed to enable maximum efficiency for on-the-fly matchmaking, combining structure and fuzzy full text search in the real-time streaming applications such as NuxX query-based XML query, XML message queues, public subscribe system for blog newsfeed, text chat, data acquisition and distribution systems, application level routers, firewall and classifiers, etc. Rather than targeting full text search in infrequent queries over huge persistent data achieved historic search, this class target full text search of a huge number of queries over comparatively small transient real-time data. Prospective search, for example, as in here. This instance can hold the most Lucene document. With the document containing 0 or more fields, each field having this name and full text value. Full text is tokenized, is split and transformed into 0 or more index terms, also known as words on add field, according to the policy implemented by an analyzer. For example, Lucene analyzers can split on white space, normalize to lower case for case sensitivity, ignore common terms with the little discriminatory value such as he, in, and n. Stop words reduce the term to their natural linguistic root from such as fishing being reduced to fish, stemming, resolve synonyms, inflections, the tertiary upon indexing and or querying, etc. Abstract Lucene queries can be run against this class. Note that the Lucene query select on the field names and associated index tokenized terms, not on the original full text. The latter are not stored but rather thrown away immediately after tokenization. Now we are considering class index splitter in package lucene.misc.index. Here we are considering Lucene 9.7.0 miscellaneous API. Miscellaneous tool. The MAIC package has various tools for splitting, merging indices, changing norms, finding high freq terms, and others. With the class splitter, index splitter, command line tool that enables listing segments in an index, copying a specific segment to another index, and deleting segments from index. Now we are considering Lucene 9.7.0 replicate API. The provides index files replication capabilities. Here an example usage of replicator. The interface replicator is in package Lucene.replicator deprecated. Use Lucene.replicator.nrt instead. An interface for replicating files allows a user or allows a producer to publish revisions and consumers to check the updates when the client needs to be updated. It is given a session token through which can obtain the files of that revision. After the client has finished obtaining all the files, it should release the given session so that the files can be reclaimed if they are not redeemed, if they are not needed anymore. Files, this is a file replication. Here this package is a file replication framework. A replicator allows publishing replicating files between server and client. Producer publish revisions and consumes update to the latest revision available. Replication client is the helper utility for performing update operation. It can be invoked either manually or periodically by starting an update thread. HTTP replicator can be used to replicate revisions by consumers that reside on a different node than the producer. The replication framework supports replicating any type of files with the built-in support for single search index. An application should publish an index revision and the index replicator handler to the client. I have on the client. For an index and taxonomical pair, the application should publish an index and taxonomical revision and set index and taxonomical replication handler on the client. When replication client detects that there is new revision available, it copies the files from the revision and then invoke the handler to a complete operation. For example, copy the files to the index directory, fsync, then reopen and index read, etc. By default, only files that do not exist in the handler current revision files are copied. However, it can be overridden by extending the client. Example usage of the replicate is here. So here the server side, writer used for indexing. Client side, either local replicator or HTTP replicator if the client and server are on different nodes. Callback invoke after handler finish handling a revision and, for example, can reopen the reader. Can also be null if no callback is needed. Invoke a client manually or periodically. Check for update every 100 milliseconds. We are now considering tools. Type this command to launch Luke. Lucene Toolbox GUI tool, a swing app for browsing documents, is index terms and posting list, searching an index and so on. Type this command to launch Luke. We can consider index format to old exception, the class. This exception is thrown when Lucene detects an index that is too old for this Lucene version. This is in package org.apache.lucene.index. As an error example, we can consider this one. Java IO exception, no sub-file with id.fnm found, etc. And here com.library.portal.search.lucene index writer.update document, etc. And here the org.apache.lucene.index.field infos, etc. And here you can see the compound file reader also.